That works. Yeah, so welcome to Leeds. Thank you. I'm glad the weather didn't stop all the transport, so it's nice and chilly. Nice to see you all here, and also great to welcome people online. Hope you can all hear okay. So I've traditionally given the first lecture in this course, and the idea is that I want to take you right back to the beginning, so kind of assuming you have no knowledge at all. But it's useful for me, at least the people in the room. How many of you have done some InSAR before? Okay, so about half, and about half haven't. So we'll try and start right back from the basics, and then over the few days you'll get in the next lecture more on time series and a few advanced topics going on, and we'll focus a little bit on the applications in earthquakes, volcanoes in particular over the coming days. Let's see. Yeah, there we go. So this is the first time I've deleted Twitter from my front slide. So this is my Blue Sky handle. That's the future, I think. This is an example of an interferogram, and for the big Turkey earthquakes that happened last year. And on the right, we've got some offset data. And what we're going to try and do over the period of this lecture, just over an hour, it will probably take, I'm going to go and explain how these interferograms are formed and how to interpret those kind of data, really starting the beginning. It's not going to be particularly mathematical, it's going to be quite sort of graphical, which just kind of reflects the way my brain thinks about these problems. Okay, so we're going to cover imaging radars. So what is a synthetic aperture? Then we're going to talk about InSAR, really the basics of how it works. What are all the different components that contribute to interferometric phase? We'll think a little bit about some of the uncertainties associated with InSAR measurements as we go through all of those different components. And then we'll spend some time at the end thinking a little bit about Sentinel-1 imaging geometries in particular, because Sentinel-1's a big workhorse that a lot of us use a huge amount of data from Sentinel-1, and it has some peculiarities. So I'm going to go way back and think about the electromagnetic spectrum. So if we're looking here, this is a log scale. We go from ultraviolet through visible light at 500 nanometers up through the thermal infrared, right up to here in the kind of centimeter to meter range, which are microwaves and radio waves. And these are the ones we use for radar. And you can see there are these weird sounding letters. The radar, as you will know, was a military technology originally. And the story I heard is these letters, K-band, X-band, C-band, SO and P-band, have no real meaning. It was just designed to confuse people. But a lot of the work we'll be doing is on C-band. So Sentinel-1 is C-band. There are some longer wavelength satellites that are L-band, and some shorter wavelength satellites at X-band that we also use for InSAR. Why do we use radio waves, radar? Well, you can look at that same spectrum on the x-axis here, going from visible up to the microwaves, and then this is plotted against transmission. How much of that light, that's all electromagnetic waves, how much of it goes through the atmosphere? So if we're at the visible, the atmosphere is pretty transparent. We can see, which is helpful for us with visible wavelength receptors in our head. But if we go into some of the reflected infrared bands or the thermal infrared bands, then there are these periods where the atmosphere absorbs all of the energy, and that's due to things like water molecules, CO2 molecules in the atmosphere, ozone, and other things. And actually, it doesn't start to become completely transparent again until we get into the microwaves. I can see we've got a hand up there. If it's a science question, I can answer those science questions periodically. What I'll probably do is pause every few slides. If it's a practical thing, do you want to ask? If you have a quick question, I can take it now. I don't know whether we can hear you. We can't hear you, but that might be, so we turned the volume down, didn't we? Let me see. Do you want to try asking that question again if you've got a hand up? Allowed to talk. Okay, hi. Ariful, SK Ariful, have you got a question or is that an accidental hand? You're muted. Okay, I'm going to carry on. Maybe put questions in the chat. If you have questions, if online you have questions, put them in the chat and maybe somebody in the room can monitor the chat.
We will, and sorry for not introducing that. There is also a possibility of using the questions and answers, so please use that. If you're online and if you have any question, please write it down. And either at the pause or at the end, we will ask directly. Thank you.
Okay, now okay, there we go. I'm back on the slide. Sorry for the interruption. Yes, so basically the atmosphere is transparent once we get above about 1 centimetre in wavelength. Get the mouse back there. And importantly, so the radio waves are not absorbed by the atmosphere, they also see through clouds. So it's an all-weather imaging technology, and that's really important for what we do. So radio detection and ranging. So initially, radars were fixed antennas. We sent a pulse of radio waves out from the antenna, measure the energy backscattered back to us, how much energy comes back to us. And then it wasn't long before these started to be on rotating platforms. So you go to an airport, you'll see a rotating antenna, and they're building up images like this. I think this particular one is a weather radar. So this is a rain front here that the radar energy is bouncing off. For remote sensing, typically we're putting those antennas on aircraft or on satellites. So what's happening is the aircraft is moving along, we're sending a pulse, we're measuring the energy back, and we gradually build up an image as the aircraft moves. And you can see in this case, we see these beautiful geological structures and nice meandering rivers, and folds, etc. So there's a lot of information there in the amplitude. So we're just looking here at the brightness of the image coming back to us. Now, there's a bit of a problem when we're using radar wavelength. And that's to do with the kind of resolution you can get and how well you can focus your image. So here's our kind of viewing geometry for a SAR antenna. And if you send a pulse out from an antenna that's W wide here and L long, then you get a footprint here, and the size of that footprint is a function of the antenna. And essentially, the key equation is that the angle that you send your beam out at from your antenna is basically roughly equal to the wavelength divided by the width of the antenna. So these two things. So this is basically telling you W is on the bottom of that equation. If the antenna is bigger, you can make a more focused beam, and if it's small, you can only have a very small beam. Very sort of the opposite of telescopes. So if you want to see something really small, you need a big telescope. That's kind of the same thing. But wavelength is on the top here, and if you remember, we're up at a meter wavelength rather than visible, or centimeters to a meter wavelength rather than visible. So if we just plug those numbers in, 5 centimeters is C-band, 10-meter antenna is about as big an antenna as you can fly in space easily. And so you end up with 0.005 radians. Now, if your satellite's 800 kilometers away, then that gives a resolution of about 4 kilometers. So pretty low resolution. So not particularly useful for getting the kind of high resolution images we'd like to get from imaging radars. So what do? This is where the synthetic aperture comes in. So rather than our single image, so this is a slightly exaggerated cartoon, but our single image, here's our satellite flying along this trajectory here. At time t2, we're imaging the ground all the way from P through to R here, so quite a wide span. So that'd be our 4-kilometer imaging footprint. If we just flip that geometry round and just think instead about a point Q, now that point Q is imaged by the pulses from all of the pulses that go from time t1 all the way through to time t3. So all of those pulses image point Q. And so essentially the trick is that we want to use all of those and try and combine them to create a simulated antenna that's much, much bigger than the one you could actually fly. So in this case, the antenna, the synthetic aperture or the simulated antenna would be all the way at this length here from T1 to T3. And in my kind of rough geometry that we did earlier, that would be a 4 kilometer long antenna. So much longer than you can actually fly in space. And the trick then is how you focus the energy. So how do you work out where an individual pulse, how do you split that pulse? So you know, okay, that bit of the signal came from that pixel, that bit came from that pixel over there, and then how do you then add them all back together? The mathematical answer is you do all this through Fourier transforms. We're not going to do this now. You'll be pleased to know, probably. But what we're going to do is then just think about what's going on. So there are two ways two things you can use. So one is you can use these contours here, these circular contours, near circular contours that are basically equal time. So if the image is acquired on one of these circles, it's basically telling the pulse came back, the bit of the echo came back at that particular time. The other thing you can use is the Doppler shift. So because the satellite is moving, when the signal bounces off the ground, there's a change in the frequency. So Doppler shift, you'll be familiar with that when a car goes past and you get the kind of thing, right, as the car comes past you. So if the signal's coming towards you, you've got a higher frequency that you hear, and if it's going away, you get a lower frequency. And the same happens with light and with radar waves. These signals here, if you're on one of these lines, you're basically there in terms of you're on the same equal Doppler. So what you can do is you can split your echo that comes back. You can do it in terms of the frequency and the time to give you exactly where it might be. Now I'm going to periodically do this and stop and ask you questions. So radars always look sideways. Why don't we look straight down? What would be the problem if we were looking straight down? Okay, I've got one here. Yeah.
Because everything would measure the same distance, we cannot then differentiate between different pictures on the ground.
Yeah, so if we look straight down, if you only looked at the point in the middle, you'd be looking at, you would have nothing to distinguish. If you were looking over a bigger footprint, you would have obviously, let's say you had this point here. We know that it's somewhere on this timeline and somewhere on this Doppler shift. The problem is we've got 2 points here. So we've got 2 points that have exactly the same time. So in order to use time as one of the axes, you have to basically be looking sideways. So you can then translate time pretty much straightforwardly into the kind of distance along the ground. Are you going to check if there's questions online, Milan? Yeah. Okay. SARs, synthetic aperture radars, are in most of them flying are in, well, I think all of them, pretty much all of them flying that I know about. There might be a Chinese one that's not in one of these orbits, but they mostly fly in near polar orbits. So that means, and they're in low Earth orbit. So they're in the kind of a few hundred kilometers above the Earth's surface. They illuminate a swath on the ground. This is a cartoon for Sentinel-1. Each of those swaths is 250 kilometers wide, and with 2 satellites, you can image the whole Earth over a period of about 6 days with the Sentinel-1 system, 12 days with a single satellite. Okay, any questions on SAR and the very basics of imaging radar? I mean, there's whole books and books you can read on this, and that's a very quick intro. I'm going to rely on Milan to shout anything that comes out online. Can you see? Yeah, there's a question here.
And when talking about the Doppler effect, there's a so-called negative and positive Doppler effect.
Yeah.
And how that integrates for creating the final result.
Yeah. So what you're doing in reality is you're looking. It's actually, when I say we also split by time, that's also done by frequency, because you send out a chirp signal in time as well. So what you do in the end is do a couple of Fourier transforms, and that can then split the data so you know where it's come from, then you add them all together. So it doesn't matter if it's negative or positive. You can basically, the Doppler will tell you, Doppler shift will tell you whether it's on that line in general. There's another number that depends on the overall pointing direction. So sometimes, particularly for the earlier satellites, they weren't looking along the zero Doppler line. They'd have a kind of average that was off center. And so there is a little bit of some complications there. But in general, well, most of the satellites, if you're using SAR data for something like Sentinel-1, you don't need to worry about any of this. You get back the image already focused as what's called a single look complex image. So you get, it's already had the synthetic aperture calculation done. So it's something you don't need to really worry about normally. Any other questions in the room? To be fine when online? Will you provide the PowerPoint in the final on the email? I think we will provide a version of the slides for people online as well. Yes. Okay. So back to the slides. Okay. So we're going to get on to the InSAR part of it. So this is a version of a slide that I first made in 1998. And it's a bit of a zombie slide. You'll see, I go to conferences and you see this slide appearing with no attribution or versions of it. The big update I made about 10 years ago was this is now a proper sine wave, whereas some of the versions you'll see are semicircles stuck together, because in 1998 I didn't know how to do a sine wave in PowerPoint. But yeah, anyway. But the idea, this is the basics of how InSAR works, right? So we've got our radar. We're basically measuring the distance between the satellite and the ground and how much it changes, right? So this is not to scale. So the satellite, this is for ERS, is at 780 kilometers. I think Sentinel's a little bit lower in the orbit, about 600, I think, for Sentinel. It's a wavelength of 5.6 centimeters. So that means there's a round trip there and back of 30 million wavelengths, roughly. But we don't know the exact number. So I guess it's a bit like having a giant ruler, and then we can know something about the phase information. So we know something about whether we've got a peak or a trough, and we can measure that quite precisely of that wave. But we don't know the exact number. So a single image by itself isn't particularly useful. We can get range information from it, but it's maybe accurate to tens of centimeters rather than the kind of millimeters that we're after with InSAR. So what we do instead is we can think about a satellite coming back, imaging the same point on the ground from a slightly different place in space. Now that will give you a phase shift because the path length is different, because we're in a different orbit. And we can measure that phase shift very precisely. Now, if we instead come back to exactly the same point in space, or imagine making some corrections, so it's as if we came back to the same point in space, and I'll talk about those corrections later. If the ground moves, then there's a change in the path length, and we can measure that change in the path length. So that's fundamentally what all InSAR is. We're measuring those small changes very precisely. If we look in practice, here's an image that was acquired on the 12th of August 1999 around the town of Izmit. This was 5 days before it was struck by a magnitude 7.4 earthquake in Turkey. And this is the amplitude, so that's just the brightness of the image. And actually, one of the amazing things is, despite this being such a different wavelength to optical data, we actually see something that our brains can still interpret. It looks kind of like, you can see that this is the sea, this is the ground. Cities look a bit bright, typically in radar images, and this structure there. The phase information in a single image is basically looks meaningless. If you ever open up your single complex image and plot the phase, so typically when you get that image, you'll have a real and an imaginary part, so you have to do a little transformation to get the amplitude and the phase. But if you do, it'll look like random noise. And that's because the precise distance to each pixel is much more variable than that wavelength. We don't have a very smooth Earth surface. So I guess you can imagine this room is maybe roughly a pixel size for some of these moderate resolution satellites, the radar's coming in, it's bouncing off all of the individual objects, well, if we didn't have a roof, imagine we didn't have a roof. It'll be bouncing off all of you. You're adding up all those individual reflections, and you get a kind of average distance to the phase center of this pixel. And that then governs the phase along with some other things. Now that's basically a random number for each pixel. If we come back, in this case, this satellite flew back over the same location 35 days later. You get another amplitude, another phase image. The essence of InSAR is we're looking at the differences in the phase. So if you subtract these two random phase numbers, you start to get out something that makes more sense. Once you've made some corrections for topography, satellite positions, Earth curvature, and we'll talk about those in detail. But once we've made those corrections, we've basically got a measurement of how the Earth has moved between those two dates. So we're seeing the deformation caused by the earthquake. If you look at that same data, but take a step back, what we can see here. So this is a satellite. Satellites are going from south to north, so flying this way. ERS imaged a ground that was about a footprint that was about 100 kilometers across, with an incidence angle in the middle of about 23 degrees from the vertical. The earthquake ruptured this fault line here, and basically one of the things that's useful, I think, to do quite often, even if you're looking at time series InSAR, sometimes go back and look at these data, try and understand what they mean. For earthquakes, if you're a long way away from the fault, you're not expecting any ground movement, but InSAR is a relative measurement. So actually the phase value here essentially is a little bit meaningless, the absolute value of any single pixel, because it depends on the satellite orbit. If you've got the orbit wrong by a centimeter, you'll get the phase will shift by a centimeter. So we only ever really think about interpreting relative movement. So we'll often think about a reference pixel. In this case, I'm going to use a reference line. So I'm going to basically say this line here has 0 phase change, and we're going to basically look at everything relative to that. If we go from here, we go through these colors, go through blue, yellow, red. This is a not to be reused color scale. This is not recommended color scale anymore. This is more modern color scales, so I apologize for that. But if we go through blue, yellow, red, we're going through one cycle of phase, and actually that has moved 28 millimeters closer to the satellite, which is half of the radar wavelength. Why is it half and not a whole wavelength of ground movement? Yeah. Yeah, exactly. Because you're basically going, it's a round trip. This image, the data is going from the satellite to the ground and back again. So if the ground moves half a wavelength closer to the satellite, the total round trip is one whole cycle of phase difference. So this is 28 millimeters of ground movement. Something strange going on here, but I will try and ignore it. If we go to the next, if we go through those colors again, we can see we get to 57 millimeters. That's a whole wavelength. We've basically got 2 interference fringes here, and we can keep going, keep counting. That's roughly 10, so about 283 millimeters. That's 20, 567, etc. We could do the same for the north. If you notice the direction of the colors, if you're counting in here, we're going from red, yellow, blue, red, yellow, blue. Here we're going blue, yellow, red, blue, yellow, red. And so we're going in the opposite direction as we're counting in towards the fault. So if they're both 0 at the end, and we look at a profile, you'll end up with something like this here, and it gradually, as you go from the south to the north, gradually increasing the bending of that line. So we've got more and more deformation. The fringes are getting closer together, it's telling you the strain, the relative motion is getting, the gradient of motion is getting stronger and stronger as we get closer to the fault. And it's the opposite on the northern side. And you'll hear much more about these kind of earthquake displacements from John Elliott tomorrow. Okay, any questions on that? That's kind of the basic level of what an interferogram is and how to read an interferogram. Anything online? How do I look again? No, okay. Is there a button I can press? I don't know what's happened here.
Oh, should we really?
There,
I found it here.
Q&A.
Oh yeah. Okay.
Okay.
Yeah. Okay.
Will you provide the
That one.
PowerPoint? Yes. How does the width of the antenna is increased? Essentially, you don't need to worry. I'm not fully sure I understand that question. You could ask that question again. We can't change the antenna size, but in terms of the resolution, that's not a long track. Basically, which maybe is what you're getting at. So the antenna is this rectangle, and we talk about the timing information. You can get, by putting out a larger bandwidth, you get basically a finer resolution in the range direction, so in the distance away from the satellite. Will you send a recorded video as well? I don't know.
Yeah, it is recorded.
Yes, we are recording it. Will you share the recording? Yes. Okay. How did you manage to calculate it? We'll talk about the changes later on. I'm confused now to how to interpret the rainbow pattern, either uplift or downward. So the colors are relative motion towards or away from the satellite, and I'll come back onto that later on. So any questions in the room? Fairly clear so far? Okay. Right. Get back onto here. Right, what we're going to now do is kind of break down. So we've got those phase measurements. What I showed you at the end was something that largely was deformation, but did have some other contributions in. But that's the result of a number of terms that make up the phase. So what we measure in the interferogram is the phase change in the interferogram. So we have the two images that get precisely co-registered together. And that's usually part of the processing to get them exactly lined up. And then we're just looking at the differences in the phase. What you actually do is a complex conjugate. You multiply the master, you multiply the primary image by the complex conjugate of the secondary image to get the phase difference and the amplitude of the interferogram. But effectively, the phase is the only thing we really usually care about. That phase contribution is actually made of a number of things. I'm going to go through them one by one and try and deal with them. We're after the deformation at the end, but we need to make corrections or assumptions about these other terms. Okay, so the first is a geometric term. This is because the satellites aren't acquired from exactly the same place in space. So we have to make that correction for the positions of the satellite. So in this simple cartoon, if these are the wave fronts coming down, you can see these bands of light and dark here. If I just make the satellites go further away, you can see there are more and more of those bands of light and dark. So essentially, the further away the satellite is, the more of a gradient of phase there is in this direction, so in the range direction. And we know the orbits pretty well now. You can calculate basically that ramp in phase. This is the biggest contribution, actually. If you look at an interferogram, the phase you get from the orbits not being in the same place is usually the biggest contribution, but we can calculate it pretty accurately. With Sentinel-1, with precise orbits, they're good to between 1 and 2 centimeters. So we can make this correction pretty accurately and subtract that from the interferogram. Anything that's left, if you get those orbits wrong, will look like quite a smooth, very long wavelength signal. So if you're interested in something very localized, like a volcano, it doesn't matter. It's maybe a bit more problematic if you're thinking about long wavelength tectonic signals, where you might want to care about those long wavelength components. But in general, for modern satellites, you don't really need to worry about this term. Anything that looks long wavelength in a modern satellite interferogram like Sentinel-1 is probably coming from the atmosphere or the troposphere or the ionosphere. So it's worth saying that InSAR isn't optimized for very long wavelengths. So if you're interested in a technique for measuring the deformation between points that are hundreds of kilometers away, then it's probably not the right tool. Okay, so we are interested in that as for tectonics, but what we tend to do is combine the power of the InSAR at the shorter wavelength with the longer wavelength control you get from GNSS. measurements, so GPS measurements. Okay, so that's it, fairly easy. The other one that's relatively straightforward is topography. So essentially, because the Earth isn't flat or a perfect ellipsoid, you get an effect, you get interference fringes just because of that topography, a bit like a stereoscopic effect in your eyes. One way of thinking about this is to think about this term called the altitude of ambiguity, HA, and you'll certainly see this discussed quite a lot in the earlier papers. Most of the time people talk about the perpendicular baseline, but essentially the further apart, so the perpendicular baseline is this term B per here, which is the distance the two orbits are apart in a direction that's perpendicular to the direction you're looking in, okay? And the altitude of ambiguity tells you how much topography you need to get a single interference fringe if you don't make a correction, or how much topographic error you need to give a single interference fringe if you have used an elevation model. And it's a function of the range, the incidence angle, and the perpendicular baseline and the wavelength. Just to get a feel for it, this is using some numbers from Sentinel-1. This is a piece of topography that's about 1 kilometer high. If the satellites are 30 meters apart, the altitude of ambiguity is 500 meters. So if we count through the fringes, blue, yellow, red, we've got about 2 interference fringes there. If the satellites are 140 meters apart, the altitude of ambiguity is 100 meters. And so we've got a lot more interference fringes. So I'm not going to try and count them, but there's more like 10 interference fringes there. In February 2000, the shuttle radar topography mission was flown, which is an 11-day mission on the space shuttle. At the time, it was the largest object ever flown in space. It basically had a radar antenna on the shuttle and one on a boom 60 meters out of the side. It transmitted from the shuttle and then measured the echoes on the shuttle and at the end of the boom with this fixed distance. And they used that data to make an elevation model for the whole planet, which is still one of the best ones out there. More recently, this has been done by combinations of different satellites. So the Tandem X mission from TerraSAR X and Tandem X flying together have also made very nice elevation models from radar as well. But that's taken longer to do. So if we want to think about the impact of getting the topography wrong, one thing we can do, we've usually got something that's at least as good as SRTM, the Shuttle Radar Topography Mission. That was accurate to about 7 meters. So if you know how accurate your elevation model is, you can work out what the phase error is from that error in your topography. So in this case, if the baseline is 30 meters, you've got that altitude of ambiguity of 500 meters. An error of 7 meters gives you a 0.4 millimeter error due to the topography. If you've got the 140 meter baseline, it will give you a 2 millimeter error in the phase. Now, these are really only important then. So these are small numbers. You can actually use a stack of images with a range of different baselines to solve for this number as well. So you can solve for this if you want. But in general, this is only important when you've got big changes in the topography that aren't captured in your elevation model. So if you're looking at a volcano, you're using the Shuttle Radar Topography Mission from data from 2000, but the top of the volcano blew off in 2010, then your elevation model might be wrong by 100 meters, and that's going to give you a problem. But if you're looking, and this is true as well, I guess the other volcanoes are one example, mines are another place where people are changing the elevation model quite quickly. The ground surface, you're getting a big hole in the ground or a waste dump that didn't exist when the elevation model was there. So then you need to think about correcting for those elevation errors. But generally, we don't need to worry about this for most applications. Use the best elevation data you can get. Right. I think one of the most challenging areas is the atmosphere, and I'm lumping two terms into here. One is the troposphere, where we get a lot of variation, a lot of turbulence, a lot of water vapor, things moving around, and that gives us problems in the signal. The other area is the ionosphere, and I'll deal with these two elements of the atmospheric contribution to noise separately. So the tropospheric part comes because we think of the speed of light as being constant, the speed of electromagnetic waves as being constant, and often we forget that that's in a vacuum, and the atmosphere isn't a vacuum. The troposphere has a lot of stuff in it, and that gives you delays to the radar wave. So this is a nice figure from a paper by David Beckart from 2015. What he looked at was data from weather balloons. So what you can do is track the pressure, the temperature, and the humidity as a function of elevation, and then use that to calculate the amount of delay there is in an individual interferogram or on that individual date. So you can see actually the atmosphere. This is from Mexico, I think. If you look at the average here, that most of the delays in the radar between an elevation of about 9 kilometers and the surface, you've got about 1.6, 1.7 meters of delay in pretty much all of those, and they look very consistent when you look at it like that. If you look instead at the differences between any of those different balloon measurements, what you get is this. And we've obviously changed the scale here. This is now centimeters. So each of these individual lines has a difference between two of the balloon releases. And so you can see you've got signals between -10 and +10 centimeters. So really big signals at this location of the weather balloon. So that's something we need to worry about. We can kind of split it up, that signal, into two elements. One is from the stable element of a stable but changing element of the troposphere. So when we've got a nice calm day, today's, I don't know what today will be like. It might be often these kind of, if you get stuck in a kind of high pressure and a nice winter's day, the atmosphere is actually pretty stable. And the general variation is with height and there's not much spatial variation. Even if that delay is then varying with height, because you've got any topography will then map into a phase delay on your individual date. So basically, there's less atmosphere and less delay at the top of the mountain than there is at the bottom of the mountain. Now, if you come back on a different day, it's still relatively stable, but maybe a different amount of humidity in the atmosphere on that next day or different pressure, then you get a different delay. And so when you look at the difference in those, you get, which is what you see in the interferogram, you get a path delay that is proportional to the topography in some way. So one of the telltale signs of this kind of atmospheric error is you've got signals that correlate with the topography. This is an example way back from my PhD days. This is before we had the shuttle radar topography mission elevation data. So this is the DM we had at the time. We had to make it, and you can see features in the topography like this triangle here, and that maps straight into the interferogram here. And you can, there's a nice valley down here. You can see also that valley maps into the interferogram. And we didn't really understand all of this back in the 90s properly. And so when I produced this interferogram, we thought we made a topographic correction wrong. But then this one here is basically the same time period, except the first image was acquired 1 day later. So this is in the days when ERS-1 and ERS-2 were flying so-called tandem mission. ERS-2 was 1 day behind ERS-1. And this was nice and smooth. It didn't have those signals. So basically what had happened here was that the atmospheric conditions on these two dates, 95 and 97, were very similar, but there was a difference in the atmospheric conditions between the 29th and the 30th of August 95. Those are relatively easy to deal with, right? It's correlated with topography. You can look for those correlations and make a correction. The ones that are harder are due to the turbulent atmosphere. So the atmosphere, if you've got much more convection going on, typically maybe you would have thunderstorms or other convective systems, you get much more complicated delays. So here's again 2 interferograms. These are both from an earthquake that happened in Athens in 1999. So this is the deformation from the earthquake. There's a little bit of noise, but not too much noise in this one. Just to get your head around again, we're going from red, we're counting down through blue back to red. That's 1 fringe. And again, 2 fringes, and we're getting back up to red in the middle. So there's about 3 fringes, in this case, movement away from the satellite, and it was mostly vertical. So about 9–10 centimeters of subsidence in this particular earthquake, magnitude 6 earthquake. This one was from June to December. This is from July to December. You can see this one looks much noisier. And when you zoom in on features, this is the one on the right is the image from June to July. And if you zoom in on features there, you can see very small scale features. In this case, 1, 2, 3 interference fringes there. This one was the first one I processed, the shorter interferogram. There wasn't as much data as we have now with Sentinel-1. And so we wonder whether those are aftershocks or things like that. But actually, because they only appear in any interferogram that uses that July date, you can tell that it's an atmospheric delay that was happening in July. And when we look back at the weather records for that date in July, there were thunderstorms in Athens. So these were big individual convective cloud systems. So again, a somewhat extreme example. You've got 10 centimeters of delay in that one very, very narrow location due to the atmosphere. But this is a common problem. The same is true with Sentinel. There's been no magic fix. One thing that's worth noting is that the descending data tends to be cleaner than the ascending data. You have bigger turbulent atmospheric signals in the ascending data than the descending data. Anyone got a clue on why that might be? Why might ascending data have more atmospheric problems than descending data? It's quite a hard one, this one. Anyone? Time of day, yes. Okay. So do you happen to know?
Ascending dusk.
Yeah. I think you back calculated that based on your hypothesis, but you're absolutely right. Sentinel is in what's called a sun-synchronous orbit. So always, wherever you are on the planet, it always acquires data at roughly the same time of day. So roughly in the morning, the descending data, dawn, roughly at dusk on the ascending data. And because the atmospheres have more time to warm up and more convection gets going, and therefore we get more atmospheric noise in the evening. Am I doing all right for questions? I haven't seen any more. Maybe there are some more. I'll come back to that in a minute. Yeah, so we just look at that. So this is Eric Fielding, who this is old Twitter data, but I'm sure he's on Blue Sky now as well. But yeah, it's 6 a.m. versus 6 p.m. local time. You do get more turbulence in the ascending data in the evening. Okay. So just to summarize the troposphere, you get plus or minus 10 centimeters of signal in extreme cases. Can be even bigger than that where there's extreme significant topography if you're looking across the Himalayas or other big structures. So how do you deal with that, the troposphere? You can ignore it, which is still quite common. And in general, if you've got a signal where you've got 50 interference fringes from an earthquake and only one of them is from the atmosphere, then maybe that's okay. It's better to, rather than ignore it, at least quantify it, try and estimate, find somewhere that maybe you're not expecting a signal, try and measure that signal and use that in your noise models when you're trying to get your geophysical parameters. You can model it based on other observations. So that might be from GPS data. GPS data are also sensitive to the troposphere. There are satellite radiometers that work in the daytime if there are no clouds. Probably the most common thing we do routinely is use weather models. So there's a weather model. There's a service called GACOS, which takes a European weather model and provides a kind of burst pass atmospheric delay. It's variable in how good that is. It won't get the high resolution turbulence, but it might get some of the long variation data. We can get that relationship with topography and make corrections based on that, or we can use time series analysis. And you'll hear more from Andy Hooper later about the time series analysis approaches. And essentially what you're doing there is you're increasing the signal to noise ratio rather than looking at an individual pair. So for a long time process, you're looking at fitting a line or fitting a step between lots of observations before the earthquake and lots after. Okay, and right, I'm going to just check if there's any questions in this, if I can. How do I move the mouse off this screen onto? Oh, I've got it going the other way. Let's see. Will such interferogram be visible for each earthquake? If the earthquake's on land, there is data usually, but sometimes there's noise signals that we'll talk about later. Yes, can you explain more what is the meaning of long and short wavelength? I think that's referring to the geometric component. So the images are 250 kilometers wide. So generally, you'll remove the things you get from an error in the orbit would be a smooth function that has a wavelength of maybe 500 kilometers that you would fit into that. So if you're looking at something shorter wavelength than that, so shorter distance, 10, 50, 100 kilometer length phenomenon, they'd be captured within a Sentinel-1 frame, and we should be able to see those okay. Let's go back to here. Any questions in the room? Okay, still with me? Okay, we're nearly there. We're nearly at the deformation, which is what we actually care about. Yeah.
I don't know how correct this question is asked, but now that we have lots of data, for example, from Sentinel-1, can we use the data itself for atmospheric correction? For example, something statistical analysis like the component analysis or something like that.
Yeah, so there's work we've been, and you'll hear later in the course. I think we got Milan, is Matt giving his presentation on the. Yeah, so Matt Gaddis will talk about a method that's not principal components, but is the other one. What's it called? It's not principal components. There's another approach that's similar to principal components.
Minimum loss fraction?
No.
Partial
Independent component analysis. Okay, which is subtly different but similar. But yeah, you can use that. What you tend to find is the deformation has the same spatial pattern or something like that, and you can try and pull that out. The challenge is if you've got something that's one-off. So if you've got an earthquake that's happened on a particular date or a magmatic intrusion, and it's time varying, some time varying phenomenon, just teasing out those components can be challenging. But you can do those data tricks for sure. And having lots of data is always great and really helpful. Yeah. Okay. I'm going to talk about the ionosphere for a second. And so that also contributes. So basically what it's doing there, you're getting what's called a Faraday rotation, which is basically rotating the phase signals. The waves are getting rotated. It's giving you an apparent phase change. Now, when you translate that into a change in distance, an apparent range change, that's a function of the wavelength squared. So if you're going from C band at 5 centimeters to L band at 20 centimeters, you've got 4 times in wavelength, but the ionosphere contributes 16 times more to L band data. And you see it, this is a cover of Nature Geoscience from the earthquake in Wenchuan in China in 2008. And all of this kind of long wavelength stuff in the distance, that's coming from the ionosphere with this L band particular mission. This was for a Japanese satellite. You also see it in Sentinel-1 though, in extreme cases. So this kind of long wavelength striking also comes from the ionosphere that you see that's in Taiwan. That's a very rare case. Usually you don't see anything that big, but you do see contributions from the ionosphere. So you can solve for that. There's an approach called split spectrum processing. So basically, because it's frequency dependent, you can degrade the spatial resolution and split your interferogram into 2 interferograms with effectively different wavelengths, and look at the differences in those to try and correct for the ionosphere. With the InSAR mission, which will be L-band, that'll be launched next year, that's actually deliberately having quite a separate frequency that it's transmitting just in order to make these ionospheric corrections. So that should be done fairly easily with InSAR. There are models globally that you can get data from GNSS. It tends to be relatively low wavelength, and we've started making corrections for those in the COMET LIXAR system. We provided ionospheric layer for some of our frames, not all of them yet. Okay, so this one, not a huge problem at Sentinel data, but it can be a problem if you're looking for very small signals. Okay, I've lumped a few things into noise, unfortunately. The main one is phase noise that's very local, and due to this term called incoherence or coherence. That's really a way we can measure the phase noise or present the phase noise, and that varies from 0 coherence, bad, to 1 being good. And we typically estimate the coherence. The coherence is a property of an individual pixel, but we can estimate it by looking at the spatial correlation of the phase between multiple pixels. So I'm representing in this diagram 3 by 3 pixels in an interferogram, with the arrow being a phasor representation of the complex data that you get back from the satellite. If you're thinking complex numbers, fine, that's the real axis, that's the imaginary axis. If not, just think about the length of the arrow being the amplitude, and the angle the arrow makes from the x-axis being the phase difference in the interferogram. Okay, so in this case, they're all pointing in the same direction, all of those arrows. What you can do is add up all those arrows, they have a length A. In that case, the phase is consistent between all of them. In this one on the right, the phase is varying in each of those pixels. You can still add up all of those vectors, and you get length B. And the coherence is approximately B divided by A. It's not quite strictly true if the amplitude is varying, but it's good enough to be true, to be a useful way of thinking about the coherence. And it is true, I think, if the amplitude is the same in all the pixels. So what this is saying is, we're basically looking at this measure of phase variability. Now, what we're assuming here is there's no real phase variability. So that the phase variability, if the deformation also varies between those different pixels, then this coherence measure wouldn't be a measure of coherence, it'd be a measure of just the variability in the deformation. And that can be a problem if you're in a high gradient area near an earthquake. But essentially, this is one way of estimating it. You can do something similar in time to get temporal coherence. Typically, people are measuring it in space. So this is the sort of mathematical relationship. So if you want to go from the coherence to the phase noise, you can use this relationship here. Now, that's basically the incoherence. So if something loses coherence, it's due to changes in the ground surface primarily. So we're talking about here, so volume scattering. So that's signals going into into vegetation canopies, bouncing around, coming back with a random phase signal because the wind is slightly different on one day to the next. It might also be geometric effects as well. I'll give you some other examples shortly. You can map it in space. It's a nice spatial property. Here's an image from Greece. You can see here's Athens, nice and bright, with plotting high coherence as white, low coherence as black. Bare rock is typically quite coherent. Buildings are typically coherent. Incoherent things are water. The water surface is constantly changing, so you don't get a constant phase back. Leafy trees are particularly bad at C-band, though they can be okay at longer wavelengths. There are things like ice, agricultural fields, grassland, might be coherent for a short period of time, but not for a long period of time. So they have a kind of temporally varying coherence. But just to summarize, it's basically a function of the surface type, the wavelength, the vegetation density, the time span, the time of year, perpendicular baseline, the changes on the ground, the weather, a bunch of things that are all folded into that. And generally, in the days, it's a little bit unpredictable. So sometimes you might get there's no obvious reason, and it's just because it's rained or something like that on a particular day and you've lost a bit of coherence. So in the days where Sentinel-1 data is available and free, then try multiple pairs. Sometimes you get lucky and sometimes you don't. But often we a function of typically longer time spans are less coherent, but not always. It's a property of space, obviously, depending on what the ground surface is. This is just a mosaic of data that we've processed over the Alpine Himalayan belt, showing the variations in coherence. If you zoom in on somewhere like Tibet, so lots of this coherence, unless you've got lakes or kind of areas of desert where sand is blowing around. You've got, if you go into the Indian part of this data set, the towns you can see are these little white patches here are the towns that are quite coherent, and the agricultural fields in between are incoherent, have low coherence. It's a rather beautiful data set, actually, but quite useful for mapping ground cover types. There are ways of improving the coherence. So this is an approach you can read more about in a paper by Spans and Cooper called RapidSAR. And the essence of this is what you're using rather than neighboring pixels. You're using pixels that are quite similar to each other. So you're finding pixels with similar brightness. And you can read more about it here, but you can get much sharper coherence. So here's a long way here, which you really don't see in the coherence when you're using neighboring pixels. Okay, so that change in the ground cover caused this random phase shift. The best strategy is you can multi-look, so you can average to increase the signal to noise ratio if you're not interested in the very high resolution. Or you can basically screen out data to remove the low coherence thing. So you want to, I have constant arguments with Milan about this. Milan likes to have more and more pixels in. I'm like, well, if I don't believe them, then leave them out. And we kind of, there's a trade-off there. I'd rather have personally, I'd rather have more reliable, fewer data, but more reliable. But there's a spectrum there. You often have to pick a somewhat arbitrary threshold. This matters because sometimes this causes what's called unwrapping errors. So the phase, we've talked about that phase being cyclical. So we were manually earlier on counting the number of fringes for those earthquakes. And that's fine if you've got a nice clean signal, relatively simple signal. You can do that counting by hand, or the computer can do it pretty well. But discontinuities or data gaps can cause phase unwrapping errors. And this means the computer basically counts wrong. Okay, and that's a problem. They're hard to deal with automatically. You can check that by doing a so-called loop closure. So if you've got 3 dates, you go from date 1 to date 2, unwrap that, and you go from date 2 to date 3 and unwrap that. If you add those 2 together, that should give you the same as if you go from date 1 to date 3. So when we're doing time series analysis, we do a lot of this loop checking. So have we made errors in any of the interferograms? And there are lots of complicated algorithms that are being developed on this, and actually some encouraging work has been done with AI to try and help with some of these, but it's a complex problem. There's also a thermal noise element. So this is something you can't do anything about. This depends on the signal to noise ratio of the satellite, how much power it has. You can improve the coherence by spatial averaging here, but essentially you can't do anything about this. You're stuck with this thermal noise. Sentinel-1 is a low noise system, so most of the noise is coming from things that are happening on the ground rather than the satellite. Okay, we got there to what we want, which is a deformation. I put this, I guess Donald Trump's back in the news, so I can make my Donald Trump joke again, but I put it in Donald Trump capital letters, okay, because it's so important. So we're only measuring the component of surface deformation in the satellite's line of sight. So basically, we're measuring the changes in distance between the satellite and the ground, and we're not looking straight down. I think if we were looking straight down, it would be more intuitive, right? Because you would just think, okay, it's uplift or subsidence. It's basically the same thing. We're just looking sideways. You just can imagine rotating the Earth around. So we have no sensitivity to movement in the plane of the wavefront. So, like I said, if we're looking straight down, we couldn't see anything moving horizontally. Right? But actually, we're not looking straight down, so we can't see any movement in that direction. So all of those vectors U basically give you the same range change delta R in this case. And it's a simple dot product, if you like. So the range change is basically if you have a unit vector pointing from the satellite, from the ground to the satellite or the other way around, then you do the dot product from the 3D displacement vector to give you the range change. If you've got the range change measured from multiple directions, you can start to invert for the real 3D deformation. Typically, we only have two directions from InSAR, so we resort to making some assumptions. So you might say, okay, we know the north-south measurement from GPS or something like that, or we assume the north-south is 0, or we know the direction of movement of our landslide, and then we can say something using the two InSAR observations from ascending and descending. We can usually say something about east-west motion and vertical motion. Okay, that equation is just turning it back into a phase change. That's basically saying one fringe is half the wavelength. Okay, any questions on those components of phase? Got about another 5 minutes to go on some Sentinel stuff. Let's just see if there's anything else online. Let's see. Go this way. Where do we get the corrections for these errors? Well, some of them you have to make those corrections yourself. So sometimes, in COMET, we provide some best guesses for atmospheric corrections from GACOS, from the ionosphere, from ionospheric models. They're not going to be perfect, so you can make those corrections. The geometry comes from the software when you're making an interferogram. That's just the topographic error. How can we perform InSAR time series analysis over croplands where coherence is lost during the summer but remains high during the winter? You basically, so I guess the facetious answer is you can't, but what you can do, you can measure the winter components, then you've got to make an assumption about how you join those up. You've got no information about how those independent ones are connected in an agricultural field because the farmer's probably come through and ploughed the field, so you've changed all the scatterers. So the randomness, so it'd be like you all moving, coming back and sitting in different seats. You get a different random number if the farmer ploughed their field. I think what you can, so you measure those winter bits. Now it might be you have a problem if the field is going up and down annually and you're only measuring part of that, you might get an apparent long-term signal that's not real. What you can do is if you're looking at somewhere like Iceland, it's probably a better example. So somewhere like Iceland covered by snow and ice for maybe 2/3 of the year. But when that snow and ice melts, the scatterers haven't moved. So like you'd be all covered by snow and ice, but you'd be frozen in place. And when it melted, you're still in the same seats. And so that random phase number would still be the same. So then you can just have long interferograms to connect your time series. You'd have detailed time series in the summer months in Iceland, and then you'd have these bridging long interferograms to get you to the next summer. You can't do that with agricultural fields without making some assumptions that might be dangerous. Okay, is there another question there? Oh, lots of questions, am I? Yes. Can you combine ascending to descending images? You can only combine the interferograms. You can't. So each orbit, you have to basically interfere satellites in the same geometry. Can we use Sentinel-1 data for monitoring mining areas with lots of changes? You can, but you just have to be careful about that topographic change. To the absolute measurement from time series, or just a relative measurement to the master image date. So one thing we try and avoid using master and slave now, and sometimes I slip up and try and use primary and secondary. It's a better way of talking about the data, and can use the absolute measurements. It's essentially a relative measurement in space and time. There are some things you can do to make it absolute, but essentially most techniques are relative in space and time. How can we check the definition of landslides? Okay, there's been more work on the signals later on. I'll let other people answer that. Can you explain the last error again and where it comes from? I'm not sure which one that one was, but it's probably the thermal noise in the satellite. That's just basically due to the more power in the satellite, the better you get a signal. I don't really have time to go in more detail on that one. Okay, I'm going to move on. Any questions in the room? Okay, we'll just move the mouse back over here. Okay, lots of satellites, ever increasing numbers. This is a few years out of date as well. Sentinel 1A and B and InSAR coming up next year. 1C very shortly. These are fully free and open, so these are kind of the workhorses for scientific InSAR. Coming up later, in a few years' time, we'll have the Harmony mission, which is an Earth Explorer 10 mission from ESA, which will be Harmony, which will be companion satellites flying around Sentinel 1D probably. And Andy might talk more about that later, but that will give you different look angles, and that will help measure north-south motion, help give you topography as well. There's a candidate mission that I'm involved in called Hydroterra Plus that might be launched before I retire with any luck. That would be a geosynchronous satellite. And I can talk more about that at another point if you have questions about it. That would require images daily, actually several images daily, which should be quite exciting. Sentinel-1, though, is a big workhorse for us, and that's the data you're using mostly. It's the first really operational C-band InSAR satellite designed for InSAR with this very essentially boring acquisition schedule. It does the same thing every time, again and again and again, which is exactly what we need for InSAR. 12-day repeat. There should be 2 satellites in the constellation, so that gives you 4 images every 12 days if you've got 2 on the ascending and 2 on the descending. It's funded for around 20 years, so we're about halfway through now. 1A was launched in 2014, 1B in 2016, 1B sadly stopped working in December 2021, and 1C is scheduled for launch 2 weeks today, so fingers crossed for that one, and that will get us back up to 2 satellites, and 1D I think is going to be launched next year to allow 1A to retire gracefully. That's what you can get from a single. This is the coverage from 2 satellites. You basically get global coverage. With 1 satellite, which we've got at the moment, the coverage is a bit more patchy, and so there are gaps. Okay, I'm getting a 4-minute timer, but you don't. We started late. Right, so data, you can download this data from the COMET InSAR portal. This is where it was, what it looked like in 2021. We had about 600,000 interferograms. By 2023, we had 1.3 million. When I looked this morning, we're getting up for nearly at 2 million interferograms there. So actually, you can get all of this data for these areas, at least, which have been our areas of focus. So tectonic areas, volcanic areas, there's very large volumes of data now that are available for you to use. I just want to give very quickly at the end a few peculiarities about Sentinel-1 data, because it's acquired in a rather unusual mode called TOPS mode. You'll see there's this step in the image here. What's happening is we're not acquiring the data all in one go, in one strip. We're acquiring it in multiple strips, like that, 3 different subswaths to give us a 250-kilometer wide data. It's not a standard wide swath where you're sweeping across like that. What it does instead is this, which is basically comes along, it's acquiring data, starting off looking backwards and then gradually sweeping the beam forwards, and then it switches to the middle swath, does the same thing, and then switches to the far swath, and then it comes back again. So you basically get that complete coverage by this kind of sweeping motion. But as you can see, it's changing the incidence angle all the time. So this took quite a lot of thinking to get our heads around what this means. And I've taken some of these slides from Andy Hooper. But we do it because you get better amplitude images. So that's why it was done. For InSAR, it's a bit of a pain, really. But there is some extra information that it gives you, as I'll show you. So let's just think about what it means for InSAR. If you're in conventional strip map, ordinary imaging mode, or regular ScanSAR, then we're always looking this direction, kind of perpendicular to the line direction of travel. So if the ground moves, or if you didn't quite register the images properly, then it doesn't really matter. It doesn't affect the phase at all. So it doesn't change the line of sight at distance. If you're doing TOPS mode, which is where you're sweeping backwards and forwards, and the incidence angle, the squint angle, this angle here is called the squint angle. That squint angle is changing. Then if you've got that rigid body displacement or a misregistration, then if you go from here to here, you're getting closer to the satellite. If you go from red to blue here, you're getting further away from the satellite. So you're getting a decrease in the line of sight here and an increase in the line of sight distance there. And that's giving you a phase ramp. And because you're acquiring it in these bursts, you get these burst-like, these ramps that look like this kind of zigzag kind of pattern. And if you put an earthquake on that, it looks a bit ugly. Now, you can, if you co-register the images properly, and I'd say 98% of the images in the LIXAR database are co-registered properly. I'm making up statistics there. Most of them are okay, some of them aren't. You can stop that beeping at me. I will finish very quickly. You can co-register this pretty precisely by actually using some of the information here in the burst overlap data. If you do that, then you can correct most of the signals. You almost don't notice it. But if you zoom in here, you can see there's this discontinuity there. That's due to the fact that there really is north-south motion in that location. It's not a misregistration. It's due to the north-south motion in this earthquake. So it's real information actually about the north-south signal. So if we account for those line of sight variations, we can deal with it. And in fact, we can use the differences of these burst overlaps to give you information about the long track motion. And the key thing is you end up with something like 1.5 to 1.7 meters of motion to give you an interference range. So that it's quite a lot of motion before you see this, but you do see it when there's large earthquakes, for example. Okay, here's some reading. You'll get these slides later, so I'm not going to read those out. These are some of the early papers on the basics, and I think it's worth going back if you're starting in the technique. Go back to these kind of classic contributions. They're quite useful. Everyone should have a favorite interferogram. If you don't, this is mine. This is from Ethiopia, from a big dike intrusion that took place in 2005. There was a relatively small eruption. These people the scale here. This is about 600 meters long at this end, but actually underground, this was about 60 kilometers long. Magma intruded all the way along that, causing this huge deformation signal. And I ended up spending about 10 years of my research career working on this as a result of this one interferogram. So it's a nice data set. And that's the Turkey. Okay, and I didn't change that at the end there. Still Twitter. So we shall leave it there. I'll take any final questions very quickly before handing over to Andy Hooper. So any questions? See if there are any online. I think most of them have been answered online. Can it detect deformation related to sediment transport by flash floods? Probably. What you might get is if the scatterers are changing, then you'll lose coherence. I guess there might be some special circumstances where you've got some kind of dune shape reflector that moves that has the same shape, but probably in general, you might just lose coherence, I think, in that question. Any questions in the room? Yeah.
So basically, many of the so the accuracy of the range is all very depends on the perpendicular baseline, right?
Yeah.
So the perpendicular baseline, for example, for Sentinel-1 is also varying. So we have like
Yeah.
30 meter to 300 meter or something like that. So how we think through this decision for which perpendicular baseline to include?
Yeah. So with Sentinel, at least for the early, until recently, Sentinel-1 was steered within a tube that was plus or minus about 100 meters. So in general, they're all more or less the same within that range. The coherence doesn't vary very much. So try everything. There'll be probably some circumstances where you really want the very small baseline. You can get that information. We provide it on the COMET portal, for example, in the metadata. You can see what the perpendicular baseline was, and then you can see if it varies, whether that is an effect that's important for your particular location.
And for the generation, then we have like the higher perpendicular baseline until Sentinel-1 is not really the first, right?
For which application?
For this elevation model.
Oh, yeah. So if you want to get the height, then you want to have something with a bigger baseline.
Yeah.
So Sentinel-1's not the right tool. You want to use something like PandomX or TerraSAR-X or Cosmos SkyMed or something, one of the X-band satellites probably, if you want a new elevation model from STAR. When we have Harmony, will be one of the things there will be to give us updated elevation models. That means when we have a volcano erupting, we can actually see that big topographic change. But so you won't ever try before that. But Harmony, I'm hoping I'll still be around. Yeah. Any other questions? Do they get a short break, or is it straight into Hooper?
Actually, it should go into Chen-Yu first.
Chen-Yu first.
The atmospheric
Okay,
correction.
right.
Yeah. So let's have indeed a pause. I think it will be fine to have 15 minutes. So until 35. There should be coffee and biscuits over there. So yeah, I would like to invite you for that. If Tim is around, maybe for some additional questions at the coffee.
I'm not going to be at this one, but I will be around at future ones. So I will be. I'm not just going to
which
love you and leave you.
Actually, the poster session, kind of improvised poster session.
Okay, very good.
For half hour. Yeah.
Okay, right. So we'll see you all later. Thank you again for coming. Thank you.
Yes,
Too much information.